Hello and welcome back to the Science of Concrete Materials class. This is lecture number 37 of the class, and here we will continue our discussion on the dimensional stability module. We have two remaining topics to cover, which are the creep and thermal shrinkage. Okay, just for the creep, a quick background. Creep can be defined as the elastic and long-time deformation of concrete under a continuous load. Generally, a long-term pressure changes the shape of the concrete structure, and the deformation occurs along the direction of the applied load. When the continuous load is removed, the strain is decreased immediately. The amount of the decreased strain is equal to the elastic strain at that given age. This quick recovery is then followed by a continuous decrease in strain, known as creep recovery. That is part of the total creep strain suffered by the concrete, as can be seen actually on this graph right here. So this is the elastic strain, this is the creep strain. This is when the concrete is loaded. When the concrete is unloaded, of course, there is a recovery of the elastic strain and part of the creep that, the concrete basically was subject or suffered, under the load. Part of the creep is irreversible, as you can see in here, okay? So the creep, as I said, time-dependent strain in hardened concrete results from applied stress. It is commonly stated that creep and drying shrinkage are interrelated phenomena because there are a number of similarities between the two. Okay, similarities to shrinkage such as the strain time curves, as you can see here, magnitude of deformation, they are on the same order of magnitude, only partially reversible. It is also a paste-related deformation. Also, as in the case of the drying shrinkage, the aggregate restrains the deformation in this case. The mechanism of the creep, as in the drying shrinkage, the mechanism lie in the changes within the calcium silicate hydrate. And it is also affected largely, by the same parameters. That, the same parameters that affects drying shrinkage on the most part affects creep. Okay. A creep is one of the most complicated phenomena of concrete. I will briefly discuss its nature and its mechanisms, for basic understanding here in these lectures. I will also discuss the factors that affect it. All the discussion about creep is going to be brief, like I said, because of its complicated nature. Maybe I will revisit the subject in another concrete class if time permits. Okay? So let's really look or get introduced to some of the terminology just to become familiar with it. We have something called the basic creep, which is basically creep without drying at 100% relative humidity, if you will. Something as you see in this curve right here. We have the drying creep. Of course, right here this is a free shrinkage, no loading. We have drying creep, when concrete is under load and also exposed to low relative humidity environment. The total strain is larger than what we account for the elastic strain, shrinkage strain, and creep strain. The drying creep is the additional strain that occurs in addition to those properties. The total creep, which is the sum of the basic and the drying creep. The specific creep, which is the basically the creep strain in relation or divided by the applied stress. It's in the range of about 150 times 10 to the power minus 6 per MPa, or 10 to the minus 6 pound per psi. These are the typical values. Okay. We also have the coefficient, creep coefficient, which is basically the creep strain divided by the elastic strain. Okay, they are explained in this graph right here. Okay. So basically, what is the mechanism of a creep? Again, briefly and very basic discussion. Like drying shrinkage, creep is in concrete likely results from the loss and the movement of adsorbed water in the hydrated cement paste, leading basically to rearrangement of the calcium silicate hydrate structure and the porosity. So in addition, with creep, there may be some additional factors which contribute to the deformation. Basically, the effects of the microcracking in the interfacial transition zone, the additional effects of drying during creep, I will talk about this in a minute, the delayed elastic strain in the aggregate, not in the paste, which also may receive more of the load over time. Okay, so these are the additional contributors in addition to the explanation of what happened within the cement paste. So the presence of a sufficient amount of adsorbed water between the calcium silicate hydrate layers may allow for a slip to occur under the shear stress. Okay, so with applied stress, water held in the micropores may migrate to larger capillary pores, resulting in a net contraction. Okay, also new bonds may form in the calcium silicate hydrate due to the moisture migration and slip as well. Okay, so what are really the factors that affect or influence creep? The first factor is the applied stress. So it is generally assumed that creep strains are linearly related to the applied stress, up to a stress of about 50% of the ultimate strength of the concrete. However, recent work and research has shown that experimental data are more accurately represented by a non-linear relationship, as you can see in this curve, and according to this equation right here. Okay, I'm sorry, let me go back. Basically, this is the strain or the creep strain, which is equal, which equals to C, which is a constant, multiplied by the hyperbolic sign of V times sigma over RT. V is the activation volume, R is a gas constant, and T is the absolute temperature, and sigma is the applied stress. Okay, according to this equation. So it is, for all intents and purposes, it's mostly of it's a non-linear relationship. However, as I said, this linear approximation for up to, again, 50% of the stress that is up to 50% of the strength of the concrete. Okay, so again, when this function is represented graphically, as we can see in this graph right here, it is found, the creep stress relationship is nonlinear, as I said, for all values of stress. But again, as I just mentioned, uh, again, approximately linear in the stress range generally used. Okay, so now the non-zero intercept for this linear representation means that even with this range, creep is not precisely proportional to the applied stress. That's the explanation, okay? But for practical reasons, a linear proportional relationship is often used, given rise to the concept of the specific creep as defined earlier, okay? Which is, as if you remember, the specific creep, uh, basically allows creep to be compared for different specimen loaded at different stress levels. And again, the typical value is about 150 times 10 to the power minus 6 per MPa, or 10 to the minus 6 per, PSI. Okay? Okay, the water cement ratio. A study of the literature provides basically conflicting data concerning the effect of the water cement ratio on creep. This basically illustrates nicely the difficulties of interpreting the creep data, since it is not possible to change one parameter independently of others. So a change in the water cement ratio of concrete means a change in cement content and the concrete strength automatically. When allowances are made for these factors, it is found that specific creep increases with increasing the water cement ratio, as you can see in this figure. Okay, so it might be anticipated that creep of concrete would be a function of its compressive strength, since basically that property is most strongly influenced by the water cement ratio. An inverse relationship between the ultimate specific creep and the compressive strength of concrete does indeed exist, basically confirming what I just said, okay? Also, the age affect creep, as you can see here. This graph, this line represents, the hydration, and this line represents the specific creep. So we know at early ages, porosity is greater. At later ages, even though porosity does not decrease appreciably, creep does, perhaps due to aging of the calcium silicate hydrate, which may improve its resistance to stress. So this is probably the explanation for the reduced specific creep with age. The temperature also influences creep. So if concrete is maintained at elevated temperatures while under load, the amount of creep is increased over that of concrete held basically at room temperature, as you can see in the figure here. Creep increases approximately linearly with the temperature up to about 80 degrees Celsius, which is 175 Fahrenheit. Okay, so where it is about three times the value at ambient temperature. Okay, but above this temperature, of 80 degrees Celsius, there is some uncertainty as to the exact relationship. Some investigators report a continued linear variation, but there are some reports of a maximum at 70 or 80 degrees, as I said. So the increased creep is a result of an increase in the rate of creep. Okay? So, and most investigators, as I said, reported that a maximum in the creep rate somewhere between 50 and 90 degrees. that, you know, the maximum of the creep rate. Okay. But the reason for these, you know, conflict in data and the existence of a rate of maximum really is not clear. But although creep develops faster at higher temperatures, the long-term creep should be lower due to aging. And again, as I explained in the previous slide, if temperature you know, there's something. If temperature increases, you know, occur while concrete is under load, an additional creep strain component has been observed that has been called transitional thermal creep, as you can see in this figure right here. Okay, so this is basically what the creep strain looks like when the concrete is loaded at 40 degrees maintained. Here we are talking about concrete at 21 degrees, and at some point in time the temperature was increased, and you see this increase referred to as transitional thermal creep. Okay, so that's the effect of temperature. Okay, moisture also affects creep. So the presence of free moisture in concrete is a necessary condition for creep. By preconditioning at a lower relative humidity before applying an external load, the amount of creep is reduced. So creep is therefore a function of evaporable water in the concrete and falls to zero when no evaporable water is present. All right? So the greatest decrease in evaporable water, and hence in creep, occurs on drying down to 40% relative humidity, okay, while water is being lost from capillary pores. So the creep versus water content relationship depends on the water cement ratio as shown in this figure right here. Okay, so this is for water cement ratio 0.65, and this is for water cement ratio 0.3. So see, this represents the approximate point at which all capillary water is removed. Okay, so basically it's, you know, higher when the water cement ratio is higher. So the amount of creep that really occurs when concrete is dried as well as loaded depends on relative humidity and time, as we can see in this figure right here. Okay, so this is at 100%, this is at 70% relative humidity, and this is at 50% relative humidity. Okay. Also, as we said, the aggregates influence creep. So the role of aggregates is similar to that in the shrinkage property. They act as restraint to reduce the potential deformations of the paste. So the aggregate content, as you can see in this figure right here, and modulus of elasticity right here, this is modulus, this is the content, are the most important parameters affecting creep of concrete. So the aggregate size and grading and surface texture basically have little influence. So there is an empirical relationship, you know, similar to that found for drying shrinkage, what we presented before, between the basically the effect of the the aggregate content rather. So this is represented right here, the effect of the aggregate content by volume, which is the letter G right here, on creep. As you can see, as it increases, you know, the creep decreases. Okay, and we have here, you know, the increase in as the decrease or the increase in the modulus of elasticity, basically how it decreases the the resultant creep strain. Okay. Also, the specimen geometry has an influence on creep. So when drying occurs while under load, the factors such as specimen size and shape become important. So the volume to surface ratio and specimen thickness affect creep in much the same way as drying shrinkage is affected, as shown in this figure right here. Okay, so creep coefficient decreases with the increase in the volume to surface ratio for the different loading durations, as you can see here. Okay. Okay, let's talk about creep recovery. Only a relatively small proportion of the total creep strain is recoverable when concrete is unloaded. It's about 10 to 20% of the total creep after loading for almost 200 days. Okay, this is the creep recovery I talked about earlier. So basically, irreversible creep dominates creep behavior, and it is of importance in predicting the behavior of concrete under variable stress. So creep recovery is strongly affected by time, temperature, and relative humidity. The proportion of irreversible creep increases with time under load. Experimental data suggests that after the first 30 days under load, additional creep strain is largely irreversible, as you can see in this figure right here. Okay, so as the time of loading increases, the irreversible creep increases as well. Okay. So the decrease, the decrease in total creep that occurs when concrete is aged before loading is a result of a decrease in the irreversible creep. So the creep recovery being almost little affected, okay? Similarly though, the decrease in creep that observed when the paste is exposed to higher temperature is the result of a decrease in irreversible creep only. So it would seem that irreversible creep can be considered as being the consequence of aging process under stress. So if the calcium silicate hydrate has been aged by prior treatment, further aging is reduced. So the drying creep and the transitional thermal creep are also irreversible, suggesting that they may accelerate the aging process. So increasing the applied stress also increases irreversible creep, but does not change the creep recovery though. So as a general rule, it can be said that the external factors that affect primarily the irreversible component, but creep recovery does depend on mixed parameters such as water cement ratio and aggregate content as well. Okay, so that's really all I have to present, or all I'm going to present about creep. I kept it short and compact discussion. Like I said, the subject is really complex and involved. I just tried to present just basic information for this level of the class. Okay. So that's all I have to say about creep. The last topic I'm going to cover is the thermal shrinkage, or thermal shrinkage. So the thermal shrinkage and the related factor, which is basically the concrete coefficient of thermal expansion, basically referred to by or denoted by the Greek letter alpha, and sometimes actually you will see it in some literature by the Greek letter mi or mu. Okay, so the length, which is the length change per unit length per degree of temperature change. It can be estimated, from the weighted average of the coefficients of thermal expansion of its components, I mean the concrete components, meaning the aggregate and the cement mortar. Typical values for alpha, for the thermal coefficient of thermal expansion of the concrete varies from 6 to 12 times 10 to the minus 6 per degree. Okay, so that's for steel about 11 times 10 to the minus 6. Okay, so basically concrete expands on heating and contract and cooling as expected. The thermal expansion, or contraction. So it could be expansion or contraction. The thermal expansion or contraction strain, which is basically epsilon sub t here, is linearly related to the coefficient of the thermal expansion, alpha, and the change in temperature as well. Okay, as you can see in this, related by this relationship right here, which is alpha times change in temperature. Okay, so so if the concrete is fully restrained, the induced stress due to the temperature change, delta T, will be equal to this value, sigma sub T, which equals to the modulus of elasticity times the coefficient of thermal expansion multiplied by the change in temperature minus the strain. Okay, so at the early ages basically of concrete usually rises in temperature as the cement hydrates. So this results in compressive stresses. But stress relaxation is high and the modulus of elasticity is low at these early ages. So the resultant compressive stress will be small and usually does not really cause any problem. However, when the concrete cools down to the ambient temperature from its peak temperature, the temperature drop will cause thermal shrinkage and may induce a tensile stress in the concrete. Okay, that's really something that you need to worry about. So in mass concrete, the difference between the peak temperature of the concrete and the ambient temperature could be very large, and the temperature drop could induce tensile stress to cause thermal cracking of concrete. And this is something that you really have to watch out for. I have seen many cases, especially in mass concrete in thick section, where thermal shock could be a problem, where the concrete or the construction teams were either lax, careless, or uninformed, uneducated by their supervisors about such a phenomena, where the teams did not take enough care to basically insulate the concrete. Because sometimes, yes, you wanna remove the forms and use them somewhere else and move on with the construction, but there are things you can do in order to make sure you dissipate the temperature rise without creating thermal shock to the concrete that will result in larger tensile stresses than the concrete's capacity at that point in time, like using insulation or whatever mitigation method is being done. So that's something you have, as I said, you have to watch out for, and you have to care about a lot, because it costs a lot of time and headache and also heartache to fix a problem like this, especially in large projects, in significant concrete construction, where sometimes repair is, as I said, really costly. Okay, anyway, so I'm gonna stop here right now, and this will be the end of the concrete time-dependent deformation, or the dimensional stability of concrete module. Next time we will start on the new module, maybe the durability of concrete. Until then, thank you for watching, and I will see you next lecture. Thank you.